Okay, so today's lecture is going to be based on cellular systems. We are going to cover some important aspects of cellular systems, because this lecture, following this lecture, you'll have 3 lectures on 3 types of cellular systems. So the next 3 lectures are on GSM, GPRS, and UMTS. So this lecture is essentially provides you some fundamental knowledge that will be taken up further in detail in subsequent lectures. So what are we going to cover today? We're going to look at the cellular sorry. Now nobody put their hand up to say that they couldn't see the screen. Okay. We're going to cover the cellular concept, and then we're going to look at the concept of frequency reuse, a bit about cell geometry, going back to what you learnt in high school, and then signal to interference ratio or carrier to interference ratio, which is an important performance measure that is used in cellular networks. Thereafter, we'll see how the most important thing that we are trying to do in cellular networks is to increase the capacity of a cellular network. So we're going to look at different ways that the capacity of cellular networks can be increased. How do cellular networks work? A little bit about traffic engineering and the generation of cellular networks. Just a brief introduction to what 1G, first generation, second generation, third generation is all about, because you're going to learn about those in more detail in subsequent lectures. So now let's see what happened before the concept of cellular systems. Imagine we have a situation where we've only got this single base station which is on, and the antenna is on top of a large tower, and you have a high transmit power on this antenna, and you're able to achieve a large coverage area. Okay, now maybe in a large city, if you have a system like this, you might be, the major problem that you'll have is as you go further and further away from this central base station, you see that the signal strength is going to reduce, and we saw in lecture 2 that there are different models that are used to predict the reduction in signal strength with respect to distance as you move away from the transmitter. So at the edge of the cells, at the edge of this coverage area, we'll find out that the signal is weak, and if you go beyond this coverage area, you find that you won't be able to communicate. So the concept of having a single high power transmitter which is mounted on a tall tower is not a good one, because the amount of capacity that you can provide or the amount of simultaneous conversations that you can have is limited. Okay, so in this particular example, they have an example here where you have a 25 megahertz bandwidth, and assuming you have 30 kilohertz that is needed for each voice communication. If you divide 25 by 30 kilohertz, we can only have a maximum of 833 simultaneous users that can be supported. Now we are going to look at some techniques in this lecture by which we can increase the capacity of a wireless network. So the way we can do that is whatever frequency band, for example, in this case we've got a 25 megahertz bandwidth, is there somewhere that we can reuse this bandwidth but at a certain distance away from this transmitter? So that's where the concept of the cellular network comes in. So essentially it was a concept that was developed for mobile radio telephony systems, because the bandwidth was very expensive and you had a very finite amount of bandwidth, and you want to maximize the use of that limited resource. So what they did was replace this single high power transmitter with lower power and short range transmitters, and each one of those transmitters had a smaller coverage area, And by using a number of these small single low power short range transmitters, you could cover the entire coverage area. So the idea was to take your geographical area and you divide it into cells, and each cell had its own set of antennas, and it had its own base station, and inside the base station you had transmitting and receiving units and control units, and each of these base stations covered a subset of the coverage area, and each of the cell was also allocated not the complete bandwidth that was available, but a portion of the bandwidth. So each cell was allocated a group of frequencies, and one of the things that we had to make sure was that when we have a number of these cells, because remember we are taking our entire coverage area and dividing it into smaller cells, we had to make sure that adjacent cells use different frequencies, because if they use the same frequency, you will have interference between them. So in non-adjacent cells, we could use the same frequency. As long as the non-adjacent cells were separated by quite a large distance, we could reuse the frequency. And this is where the concept of frequency reuse comes in, because the band of frequencies that we are using in one cell is essentially repeated at another part of the coverage area, and that way, in this manner, we can increase the capacity that we have. Now, one of the consequence of having a cellular network, which is dividing our coverage area into small cells, is that as a user moves from one cell to another cell, we have to make sure that the user is always connected to the best base station. So there was a need for handover mechanisms as users move from one cell to another, and because of this, you also had to incorporate inside the mobile phone mechanisms by which it will take measurements of all the neighboring cells and report these measurements continuously to the network, and the network will then decide what is the next cell that is going to serve a particular mobile station. So the consequence of having a cellular network is that we need handovers, and the other thing that we also need apart from handovers is we need to know which is the cell that a current user is located in. So we need to know the location information of users, because when we have a mobile terminated call, that is a call that is coming to a mobile, we need to know which cell that particular call should be switched to. So in order to do that, we need to know location information of mobile users as they move inside a coverage area. So even when you're not making a call and you're moving around, your mobile is constantly reporting its location by means of an area. It doesn't have to know the precise XYZ location, but it sort of reports which is the current cell that it is, or a group of cells referred to as a location area within which it is located. And this information is used for mobile terminated calls. So cellular networks are consequently far more complex than fixed wireless networks. So how is it possible that cellular networks can work? Well, we saw this diagram earlier. We saw this in lecture 2. We said the transmitted power reduces quite rapidly with distance as you move away from. This is an ideal graph, but in reality, the graph will be a sort of a variation like that, a rapid variation. It won't be a nice curve like that. But as we move away from the base station, the signal strength will rapidly drop, and there comes a point at which the signal strength is so small it is equivalent to noise level. Okay, so at this point, essentially what we can do at this point is that we can, when we receive when we start getting to these kind of distances, we can start repeating or reusing that particular frequency, because the point at which this frequency was used before is so quite a distance away, and the level of interference that it creates is so small, it is probably the same as noise level. But we have to make sure that this distance here, which is the distance at which we reuse the frequency, has to be planned very carefully. So essentially power levels decrease with distance. Now there's a power level trade-off here. Obviously, if you use high power, you're going to have a better performance within the cell. But the higher the power you use, the more the interference it will create at another point where you're going to reuse the frequency. And if you use a lower power, you're going to have less interference on the same frequency. And this is referred to as co-channel interference. So in the concept of cellular networks, you'll hear two terms: co-channel interference and adjacent channel interference. Co-channel means when the frequency is reused on the same channel, what sort of interference does it create? So if we go further and we describe, try to define what a cell is, one definition of a cell, there are many definitions that you can find in textbooks, but one definition is a coverage defined area within which a number of radio frequencies is used. Okay, so a cell is essentially an area within which a number of radio frequencies or channels are used to carry data and data traffic and control signaling. The other thing that each cell has to do continuously is, remember we said earlier that the mobiles have to make measurements. So in order to make measurements, mobiles have to identify cells. So in order to identify cells, each cell has to have a beacon channel or a control channel on which it communicates with all the idle mobiles that are there. So on this beacon channel or control channel, it broadcasts information. So each cell has certain identifiers, a cell identifier. It has information about what sort of power it is transmitting it and so forth. And these beacon channels, whatever information, whatever system information that is transmitted on these beacon channels are picked up by the mobile, and the mobile uses this to update its location. So once a mobile gets locked into a particular base station and it knows the channel identity of that particular, the cell identity of that particular cell, when it goes across the cell boundary, it will see that the beacon channel it is now receiving is a different cell identity to the one it had before. So at this point, it can know that its location has changed, and it reports that to the network. So a whole bunch of information. There's quite a lot of complex information that is transmitted on the beacon channels, which is constantly monitored by the mobile. So apart from the beacon channels or control channels, you also have channels on which are referred to as traffic channel, on which all the user traffic is carried. But the traffic channels are only allocated to a mobile once you are sure that this call is going to be taken up. So for example, when you make a call to somebody, you're not actually allocated a time slot at the beginning of the call, but all of the signaling that takes place on the control channels, and only once the person at the other end answers the call, you're allocated the time slot which you use for your traffic. Okay, so this way you can maximize the use of your traffic channels. Now this can also create problems, because in certain countries, like the control channels are also used for SMS, for example. So I know in some countries, I think it was the Philippines, where when they first rolled out some of their networks, the number of SMSs that were sent were so large that they blocked the entire control channels. And because the control channels were all blocked up, people's requests to make a call were not getting through. And all the traffic channels were just sitting idle and not being used. Okay, so it does create a problem in that sense, but this is where engineers that are working in mobile operator companies have to dimension the amount of traffic channels and the amount of control channels appropriately, so that blocking does not take place in both the control channels as well as the traffic channels. So what factors determine the size of a cell? Well, cell sizes can vary from small cells up to about 100 meters in cities, inside buildings, inside airports. You will have very small size cells inside shopping centers where there's a large capacity. Whereas as you go out to the countryside, you might have cells that are much larger in size, maybe up to a maximum of about 35 kilometers in the case of GSM. So the size of a cell is essentially determined by the propagation loss and also the propagation delay. Propagation loss, because if you're transmitting at a certain power, you know after you go a certain distance, the received signal will become weak and it might not be understandable by the mobile phone. So there's a receiver threshold associated with each mobile, and once you go below that threshold, the mobile will not be able to decipher the message that is sent. The other aspect is also propagation delay. There's also, in some cellular networks, there is a maximum delay that can be tolerated by the network. For example, in the case of GSM, because we use something called timing advance, there is a maximum distance associated with the cell size. Now, in real life, the actual size is determined by the number of the traffic on the network. So usually in areas where there is a large traffic capacity or large number of users, the cells will be smaller in size. And in areas like in the middle of cities, whereas as you move away from the cities, the cell sizes will become larger and larger. Okay, now in CDMA-based systems, the cell sizes can change with respect to time, and this is referred to as cell breathing. So sometimes the cell can be large, and sometimes if the cell gets loaded, the cell becomes smaller in size, and this concept is referred to as cell breathing. And this is a concept that's associated with CDMA-based systems. Okay, here is an example of what sort of, when you're looking at a cell, the important things are: what is the radius of the cell, what are the transmission powers that you can have, what are the delays you can have, and so forth. So you can see that in this particular example, you have something called a macro cell, and you've got something called a micro cell. So in a macro cell, you've got large cells and consequently large transmit powers. And in a microcell, you've got smaller cells and a much smaller transmission powers. Obviously, the maximum data rate that you can achieve in a microcell will be much higher than that in a macrocell. Okay, we're going to move on to the next topic in this lecture, which is looking at cell geometry. Okay, how do we represent cells? Well, if you look in most books, you are going to see cells represented by hexagons. And the question is, why do we use hexagons? Why can't we use circles, or why can't we use a square or a triangle? There are only three polygons, three regular polygons, which are squares, triangles, or hexagon, that can form a closed pattern when you put them next to each other. So these are the three shapes that we can use to represent a cell. But the hexagon is the one that is mostly used because you can if you look at first of all, a hexagon is the one that comes closest to a circle. Okay, because remember when you have the concept of cellular network and we have base stations at the center of a cell, we find that a circle best describes the points at which the powers you have equal received power, and the hexagon is the one that comes closest to that. If you use something like a square, okay, if you have a square based cell, we find that this distance here, assuming that the base stations are in the center of these polygons, we find that this distance here is going to be much larger than this distance. It's the only shape in which the centers of the adjacent polygons are equidistant from this one is a hexagon. No other polygon satisfies this particular criteria. So you see that hexagons are the ones that are primarily used for representing cellular systems. Now in reality, although hexagons are the polygons that are used for representing a cellular network, in reality there are no hexagons drawn in real life. Okay, hexagons are just a way of approximating a cell. In reality, if you look, the cellular coverage will be odd shapes like that, okay, because remember the ground is a three-dimensional thing, okay, so when there are valleys or when there are trees and all that, the coverage area gets distorted. So in reality, if you have base stations out here, the coverage of base stations will be irregular shapes as shown in this diagram. But to do all of the calculations that we need to do, we use hexagons as a means of representing cells. Okay, now we've talked about the idea of frequency reuse. Okay, we said that frequency reuse essentially means that the same transmission frequencies that are used in a particular cell can be reused in non-adjacent cells. Okay, we don't put it in adjacent cells. We've got to make sure that it's used in non-adjacent cells. So whenever we reuse a frequency, the original frequency interferes with the point at which the frequency is reused, and this is referred to as co-channel interference. Now, one thing that we have to do in cellular systems is, as opposed to fixed wireless systems where we are trying to transmit as higher as possible power, in cellular systems that is not the thing. We are trying to actually minimize the power to an acceptable level. So we got to make sure that the transmission power that we transmit in cellular systems, we try and put it at the minimum possible power, such a way that it does not interfere with adjacent cells at which we are reusing that particular frequency. Now, in order to express this co-channel interference, the performance metric that's used is something called carrier to interference ratio, or SIR. Okay, so later on we'll derive an expression for this term here. Okay, so remember, carrier to interference ratio, we'll come across that later on because it's used to express the relationship between the carrier signal and the interfering signal. The interfering signal refers to one at which the frequency is being reused. So why are we doing frequency reuse? Well, the main reason we are doing frequency reuse is to increase the capacity of a cellular network. Okay, now another term that you'll also come across is something called frequency reuse factor, which is also referred to as cluster size sometimes. So these two things mean exactly the same thing: frequency reuse factor and cluster size. So okay, there's an example here. The other thing that you'll also come across is the concept of frequency reuse distance, which refers to the distance at which you are reusing a particular frequency. Now here's a bit of geometry. Now this is something that when you put hexagons next to each other, there is an equation. This is probably an important equation. Okay, now the derivation of this equation is given in the appendix. And again, I'm not going to ask you to derive this equation. The only thing that you need to know is you should know how to use this particular equation. Okay, the D here, capital D, refers to the distance between centers of cells in which the frequency is reused. So the distance between centers of co-channel cells is this capital D. The R is the radius of a cell. Okay, so this ratio here, D over R, is an important ratio. It is used later on. We'll see how it is used to measure the carrier to interference ratio of a cell. Okay, let's do some examples, because this will probably illustrate. Imagine that we have three frequencies. Okay, we've got frequency F1, frequency F2, frequency F3. So we're using, in this particular cell, we're using F1, in this cell we're using F2, and this one we're using F3. So these three frequencies are being reused. Okay, so F1 is reused here, here, and here. So you can see that it's being reused in non-adjacent cells. Now, in this particular case, remember that equation that I showed you earlier, that D over R equals square root of 3K. Okay, so in this case here, K is equal to 3. So D over R equals 3. Okay, so what I mean by that is, if you look at this distance here, this distance here represents the distance D at which you are reusing the frequency, and this distance here represents the radius of the cell. Okay, so the ratio of this distance at which you are reusing the particular frequency F1 to the radius of the cell is given by square root of 3K, and in this case is 3. And you can see that quite well, because if you look at that, there's one R there, there's another R here, and there's a third R here. So in this case there is 1 R, 2 R, 3 R's here, so there's 3 R. The ratio of D to R in this particular case is 3. This is a simple frequency reuse. Another possibility is to use K, so a K value of 4. So here we are using a frequency reuse factor of 4. So we have frequency 1 being reused in those 4 cells here. And in this case, the ratio of D over R will be square root of 12. Okay, which you can work out. And you can prove that mathematically as well from your knowledge of hexagons and the geometry associated with them. Another possibility is to have K equals 7. Okay, so here we are using 7 frequencies. Okay, label 1 to 7, and we are reusing them. So the frequency that's used in this cell here is repeated in this cell, this cell, this cell, this cell, this cell, and this cell, and so forth. And here, if you were to work out the D over R ratio, what will it be? Square root of 21. Okay. that is that's something that you can work out. So remember that formula that I told you earlier, D equals okay, so this is the formula that I showed you earlier, and this is the same one that we're using in this particular case. Okay, this is another colorful version of the same slide. So in this particular case, when we use a frequency reuse factor of 7, which is a very popular frequency reuse factor, we see that a particular frequency is reuse 2 cells. There's at least a 2-cell radius between the point at which it is reused. We can also have much higher frequency reuse factors. This diagram here shows frequency reuse factor of 19 and so forth. Okay, now in reality, okay, the ideas that I showed you about was the ideal or the theoretical case. In reality, things are not exactly don't conform to this, because you don't have a choice of where you can put your base stations. Okay, most of the time your base stations are already fixed in certain locations, so you have to work with those sites. You can't just put your base station wherever you want to. So the location of the base stations is in some way fixed, and there are also geographical features on the ground. So you might have hills and trees which will affect the shape of your cells. Also, you might have, instead of having omnidirectional antennas cells, you could have sectorized cells. And when you have coverage, when you are providing coverage in a city and when you are providing coverage on a road, the sort of coverage that you provide will be different. Okay, so these are factors that will make the way you plan a network different to reality from the ideal case. The other thing that also happens is we talked about frequencies being fixed to specific cells. Okay, that's called fixed frequency assignment, that you assign a set of frequencies to each particular cell, and it stays assigned that way. Now, the only problem with this fixed frequency assignment is that, if you look at the pattern that we showed earlier, where we assign frequency 1 to this particular cell, frequency 2 to another cell, frequency 3 to another cell. What if we have a situation where the load in one cell is much higher than the load in the other cell? Okay, maybe there's no traffic on one particular cell. So in that case, that frequency is not being used efficiently. So you might have a situation where frequencies, most of the time you don't have fixed frequency assignment nowadays. You have dynamic frequency assignment. That means frequencies, base stations choose the frequency, or base stations are allocated frequencies based on their load. So initially, base stations may have a small set of frequencies that they allocated, but when the load in a particular base station rises, they may be allocated more frequencies because they're having a high load. So dynamic frequency assignment is the one that is more likely to be used. And again, the networks are constantly making interference measurements, and these are being reported, and this is what is used to dynamically allocate frequencies to various cells. Okay, and also there's also a move now because we have less number of base stations, there's a move from omnidirectional sites where you have one antenna to sectored cells, maybe with 3 sectors or 6 sectors, and with these we can achieve a much larger coverage with the with one particular base station site. Okay, so when you have, for example, in the case of an omnidirectional site, we might have 3 frequencies allocated to a particular one. These are probably more likely to be used in rural areas, whereas as you move towards the centers of cities, you'll find that sectored cells, maybe in each sector some of the frequencies that are allocated to each sector, thereby creating 3 cells in one particular site. When you have roads, say you have a road like that, the dotted line here showing a road, you want to make sure that most of your coverage is along the road, because it's very unlikely that these areas on the side of the road could be farms, and there's going to be very little subscribers on those farms. So when you plan for coverage along a road, you make sure that you point your antennas in the direction of the road so you can get most of your coverage within the road. And you'll also see in tunnels, if you see when you go down one of the tunnels in Sydney, the Harbour Tunnel or any of the other tunnels, you'll find at the entrance to the tunnel you'll have antennas pointing towards the tunnel, because they are trying to get coverage into the tunnel, because you don't want your to drop a call when you're going through a tunnel. So again, in that particular case, you're trying to get highly directional antennas put in roads and tunnels to make sure that your cell is shaped within the it follows the road most of the time. Okay, now we talked about carrier to interference ratio. The carrier to interference ratio is a way of determining the performance of a cellular network. So the carrier to interference ratio is essentially the carrier power to the interference power. The interference comes from the fact that you are reusing that particular frequency, and what you are trying to achieve is a high carrier to interference ratio. Okay, how can we obtain a mathematical expression for carrier to interference ratio? Okay, again we go back to our diagram here, where cellular network, which is approximated by hexagons, and in this, if this is the cell in which we want to work out what is a carrier to interference ratio that we can achieve, and these other orange cell represents the cells on which the frequency is being reused, or these are referred to as disturbing cells because of the fact that the frequency is being reused in them. Now we want to work out what is a carrier to interference ratio, which will be a ratio of the useful signal to the signal from the disturbing cells. So the best carrier to, obviously very close to the, assuming here we have omnidirectional sites at the center of the hexagon. As we move away from the center of this hexagon towards the edge of this hexagon, we see that the carrier power is going to decrease. Okay, the carrier power is going to decrease and decrease, and the interference will keep increasing because you're getting closer and closer to sources of interference, which are these cells here. So in order to work out a mathematical expression for carrier to interference ratio, we have to look at the edge of the cell. So we might choose a point that is furthest away, say one of these points here. Doesn't matter which point you choose, because the mathematical expression that you'll obtain will be the same. So you choose a point that is furthest away from the base station. So in that case, we see that the power that is received from the base station is PO, which is the power transmitted by the base station, R to the power minus alpha. Where we saw this expression, we said that the as we go further away from the base station, as R is the distance from the base station, as we go further away from the base station, the signal strength reduces by this coefficient here, path loss coefficient. So here the power will be P R to the power minus alpha, and we also have to work out the signal that is obtained from the interferer. Now in this particular case, the interference will be made up of two things: a neighborhood cell interference and noise. Now to work out this term here, neighborhood cell interference, we have 6 neighbors. Okay, so if you take these 6 neighbors, and this is where the sixth term comes in here in this equation. And you say if all of them are also transmitting with the same power P0, and this D here represents, can be approximated by the distance between cells. We talked about this earlier, the distance at which the frequency is being repeated. So in this particular case, it represents that distance there. Okay, and so we have 6 terms from these 6 interfering sources. So now there's quite a lot of assumptions that they have made to get a simplified expression. So if you neglect the effect of noise, and if you assume that remember we are considering a point here at the edge of this cell, this we are approximating it to capital D, so that's why you have 6 terms from the 6 interfering sources. And if you neglect noise, we get an expression for the carrier to interference ratio. So the carrier to interference ratio, again, there are a lot of assumptions in this equation, but it's a simplified form. It gives us an idea of what the carrier to interference ratio depends on. We see that if we assume that we can neglect the effect of other noise, and if we assume that all the base stations are transmitting at the same power, and if we assume that this distance, capital D, is much larger than the distance R, then we can obtain an expression for the carrier to interference ratio. So the carrier to interference ratio is given by this expression. So it's directly proportional to the size of the cell, and it's inversely proportional to the distance between cells. Okay, there is an example worked out here, and when you get these slides, I'll put it up on UTS Online after we finish the lecture here. But they've given an example here, and they've tried to go through a worked example in which they work out the carrier to interference ratio. Okay, now usually you see that I think the important point is that there is to get good quality speech, you need a carrier to interference of about 18 dBs. Okay, that's the normal number that is used. And if you put that back into this equation, we find out that the only way that we can achieve an 18 dB carrier to interference ratio is to use a cell size of 7. Okay, so only at a cell size of 7 we start achieving a carrier to interference ratio of about 18 dBs. And that's why the term 7, the 7 hexagonal frequency reuse pattern is used quite often. Okay, I think we should possibly take a break, and then when we come back, we'll carry on. Okay, so the next thing that we're going to look at is how do we go about increasing the capacity of a cellular network. Okay, it basically follows from the exercise that you've done. Okay, there are 5 important ways of increasing capacity on a cellular network. The first possibility is adding new channels. Obviously, if you can get more bandwidth, we can have more channels, and if you have more channels, then we can carry more traffic on our network. But bandwidth costs a lot of money, and operators might have to buy the bandwidth from the government to have more channels, and that might not be a solution. Another possibility is something called frequency borrowing, and this follows from the idea of dynamic frequency assignment. Instead of allocating frequencies permanently to cells, we only allocate frequencies when we need, or maybe if one cell is not using its frequencies that well, maybe it can borrow some of its frequencies to neighboring cells. The third possibility is to use something called cell splitting, and we'll have a look at that. And the fourth possibility is something called cell sectoring. We talked a little bit about cell sectoring, where we replace some of our omnidirectional cell sites with 3-sector or 6-sector cells. And the last possibility is to use something called microcells, macrocells, as a way of improving the amount of capacity that we can carry in our network. So we'll have a look at each one. First thing is to use something called dynamic frequency assignment. So the earlier way of doing frequency allocation to cells was called fixed channel allocation. Basically what that meant was that each cell had a fixed allocation of channels. And this was not a very efficient way of using the expensive frequency resource that you had, because you could have one cell that is highly loaded and using all the frequencies that is available in it, and you could have a neighboring cell where maybe there's not much traffic and the frequencies are not being used much in that cell. So it's a simple to use strategy, because when you're planning it, you plan it and you put all the information into your network planning tool, and the frequencies are allocated to various cells, but it is not an efficient system. The second possibility is where you borrow cells. So for example, each cell gets allocated a group of frequencies or a group of channels, and it borrows to its neighbor whatever frequencies that it is not using when the neighbor is getting congested. So essentially what happens here is that heavily loaded cells will borrow frequencies from their neighbors and use them. An alternative of simple borrowing is called simple hybrid borrowing, where you allocate one set of frequencies are fixed. So the frequencies labeled A0, B0 and C0 are fixed allocations to cells A, B, C, but there's another group of frequencies A1, B1, C1, and these can be borrowed among the cells. So again, we split the channels that we have available into fixed and borrowing groups, and the fixed groups remain permanently allocated to a cell. Another possibility is not allocate any frequencies to any cell. So all of your cells initially will not have any frequencies, and you have all of the frequencies represented by A, B, C on this slide as being in a pool. And whenever traffic starts arriving at a particular cell, you start allocating, the network management tool starts allocating frequencies to each particular cell. So here in this case, there's no fixed relationship between channels and cells. Any channel can be allocated to any cell. And obviously, once a call is completed, the channel that was allocated goes back into the pool, and it will be allocated maybe to another caller in another cell. And a hybrid channel allocation schemes is again one in which you have one pool of frequencies that are permanently allocated to each cell, and there's another pool of frequencies that is available for use by any of the cells. So here we have again the concept of a fixed set and a dynamic set. So this is one technique of improving the capacity, because what you're trying to do essentially is you have this available bandwidth or available frequencies which is very limited, and you want to try and maximize the usage of that limited resource. Okay, the third way that you can increase the capacity is by using something called cell splitting. So what you may have is, if this 7-cell pattern was the original pattern that you started off with, and then you found out that in these areas here, this area here which has now been highlighted, you find out that there are more and more calls being made in that area. Maybe a new shopping center has come up there, or maybe there is something happening in that geographical area which is causing more traffic to arise. Maybe there's an important road intersection there, and more cars are stopping there, more people are making calls from those cars. For some reason, more traffic is arising in this particular geographical area of your coverage area. So what you do is you start splitting this area into smaller cells, similar to what we did here. We saw that when we start taking a large area and we start splitting them into smaller and smaller cells, we can carry more traffic overall on the network. So this is called cell splitting, where geographical areas where you have larger traffic are split into smaller cells, and by splitting them into smaller cells, you can essentially carry more traffic in them because you're better utilizing the frequency band that you have. So you might have a situation like this. For example, this could be the CBD. The green area here could be a CBD area where there's a lot of traffic and you have very small cells. As you go away from the CBD area, the cells become larger because there's less traffic in them. And as you go out of the city area to maybe a rural area, the cells become even larger. So the size of cells, you could have smaller cells, very small cells in CBD areas and much larger cells out in the rural areas. A fourth way that you can increase capacity is referred to as cell sectoring. So here we create sectors, okay, and by creating sectors and by using highly directional antennas in those sectors, we can achieve an increase in capacity. Okay, so there are different ways that you can increase capacity. This pattern here is referred to as a 4/12 reuse pattern with 3 sectors. Okay, so here in each one of these blue points here represent base station sites, and in each base station site there are 3 sectors, and you are essentially you're able to create a 12 sector pattern and reusing frequencies in every 4th base station. Okay, this is another pattern, another frequency reuse pattern that is referred to as 3/9 frequency reuse pattern. Okay, now with the cell clustering, the more the sectors that you can have in a cell, the better the carrier to interference ratio you can get. Now I didn't want to go through the mathematics of the derivation of this, but if you look at any standard text, they will show you how if you have a 7-cell cluster with 6 sectors per cell, you can achieve a carrier to interference ratio of 29 dBs. And with 4-cell cluster with 6 sectors per cell, you can achieve a carrier to interference of 26 dB. So essentially by having this sector concept, you can obtain better carrier to interference ratio. The 5th way that you can improve the capacity is to use something called microcells. So you have 2 layers of cells. You have macrocells that provide coverage for larger areas, and you have microcells usually located much lower in height. So you might, whenever you see antennas on the sides of the building, not right at the top, usually antennas that are on top of buildings are for larger cells, macrocells, and antennas that are placed on the sides of building, much lower in height, can be used to achieve microcells or smaller cells. So you move your antennas from the top of hills and top of buildings to the sides of buildings and even lampposts, so that you can have a smaller cell, which are referred to as microcells. So sometimes you will have on the same area, you might have a GSM network where you'll have smaller cells called microcells superimposed on larger cells called macrocells. And sometimes when you're moving fast, say when you're moving in a car, the network will detect that you are moving in a car, your velocity is high, and it will move you to a macrocell because you need a larger cell when you're moving faster, whereas when you're walking, when you're a pedestrian walking on the road, it'll detect that your velocity is not that high, and it'll keep you on a microcell. So there is also handovers that it can do from microcells to macrocells in order to achieve better coverage and better capacity. So the whole idea of moving your antennas to the sides of the buildings is to create smaller cells, because you know that especially in a CBD area, if you bring your antennas down to the sides of the building, the cells that you will create will be much smaller than if you put your antennas on the top of the buildings. Okay, so this brings to the concept of a macro-micro cell overlay, where you have two different networks. Each network has cells of different diameters. The macro cell diameter is much larger, and the micro cell cell diameter is much smaller. So microcells can be used in areas where you have a lot of traffic, areas like airports, railway stations, shopping centers, where there's a lot of traffic there, and you want to create small area cells which can service your customers better, then you would use something like microcells there. Okay, now you can also go further down to picocells. Okay, so from macrocells to microcells to picocells, which are even smaller. Okay, and these could be much smaller, lower power cell sites, either wall or ceiling mounted. And sometimes you could have something called a leaky feeder. Okay, essentially a feeder which has through which electromagnetic waves can leak out, and just a feeder that might be running above the wall or above this ceiling, above this fake ceiling, and that can radiate enough electromagnetic waves so that people in this area could get coverage from that. And these are also used for tunnel coverage. So again, a simple way of providing, the whole idea is with these picocells, you want to try and make sure that the power is as small as possible, because by making the small power, the transfer power as small as possible, you make your cell as small as possible as well. And that's the whole idea, making small cells where you have you can have large capacity. Okay, so that's 5 different techniques that can be used to improve the capacity of a cellular network. There are also other techniques that are used, but I'm not going to go into those ones. Now, how does a cellular network work? Okay, so now we know we have the concept of base stations and base stations that are distributed throughout your coverage area. How is it possible for users to make calls on this? Okay, so we'll talk a little bit about this, and some of the concepts that I'm going to talk about here are generic enough so it can be used in both 2G or 3G networks. But essentially, all users communicate with a base station over what is called the air interface, and from the base station, the signal travels through a number of nodes to a switching node, which is referred to as the mobile telecommunication switching office, or MTSO. In the case of GSM, this is called an MSC, but the generic term for this unit that does the switching is called MTSO. So if one mobile is communicating with another mobile, the information goes to the MTSO, where it is switched back to another base station and down to the user. If the user is communicating with somebody on the PSTN network, then the call is switched through the PSTN network to the subscriber on the other end of the network. So the 2 most important components in a cellular network are base stations and the switching office. There are usually many other components, but these are the 2 ones that are, whether you look at first generation, second generation, third generation mobile network, they all have base stations and a switching center. The channels that are available are referred to as control channels and traffic channels. So all of the signaling takes place on control channels, and all of the traffic, the user traffic, is carried on the traffic channels. So in a base station you have antennas, usually pretty high as possible. Okay, it depends again on the type of cell that you are trying to achieve. You have transceivers, and the base station also has to have a link, either a wired link or a wireless link, through which it communicates back with the switching office. The switching center is probably the most expensive unit. The MTSO or the MSC is the most expensive unit in a mobile network, because all of the calls have to be switched by the switching center. So all the base stations transmit the information to the switching center, and the switching center initially receives the instructions from the user and switches the call. It also, the switching center, especially in second generation mobile communication system, all of the handoff decisions are made by the switching center, and it also has to monitor the calls and detect when a call is terminated, and it performs a billing function. Okay, so what sort of stages does a call go through? If you look at it diagrammatically, probably this diagram is the best to go through. Now, when you make a call in a mobile, in a cellular system, the first thing that happens when you switch on is that your mobile has to scan all the channels that are out there, and it will select the strongest one, because usually the strongest one means the one that it's closest to, but not always, but most of the time the strongest signal that control channel that you can pick up is the one that is the best one to use. And as soon as you pick that up, there's a handshaking procedure that goes on between the user and the network, where the user might have to register and be authenticated. And once the user is authenticated, the user is ready to make a call. And after that, as soon as the user even after the user is handed over, it has to continuously scan the channels to see if it has moved into a new cell, and if it has moved into a new cell, some sort of handover procedure needs to be handled. So the next thing that a user might do is make a call. So at this point, the user has established a connection with the base station, and the user requests a control channel on which it can do the signaling to make the call. And the request for the control channel, the base station allocates it a control channel, and the user dials a number that it wants to dial. That number is sent to the that number that is dialed is sent to the switching office, MTSO. The MTSO then checks its database. The MTSO has access to a database of all the users and which location they are located in. And if it knows that, okay, this particular user is located within these particular 7 cells, it will send a paging message to each one of those base stations. So in this case, there are 7 base stations here. All 7 base stations will get a paging message from the switching office, and the paging message is sent on the control channels by each one of those 7 base stations. And all the users are continuously monitoring these paging channels or these control channels. And when they see, okay, somebody is trying to contact this particular user, it will respond and say, okay, I'm in this particular cell. Okay, so the mobiles, even when you're idle, as soon as you switched on, they have to be continuously monitoring all of the paging channels to see if there's an incoming call for them. Once you accept the call by pressing maybe the answer button on your phone, that indication is sent to the base station, and it is only at that point that the mobile MTSO knows that this particular subscriber is located in this cell, and the MTSO then will then instruct the base station to allocate channels, traffic channels, to both the calling user as well as the call user. And that's when the communication begins. So until the point at which the user answers the call, all of the signaling takes place on control channels. No traffic channels is allocated to a user because traffic channels are an expensive resource. So when the call is answered, a circuit is set up, and then after the circuit is set up, the call starts, and the MTSO is continuously monitoring to see if one of the parties have terminated the call, at which point a billing message will be sent to your billing center saying these two users have been communicating for so many seconds. Okay, the other thing that will happen is while the users are communicating, it's also possible that one of the users could move into an adjacent cell. Okay, so that is, as I said earlier, that is a handoff procedure, and this is another function that the switching center has to do. When a mobile moves out of the original cell and into the coverage area of another cell, this mobile will detect. Now, this mobile, as I said, is continuously measuring the channels, the beacon channels of neighboring cells, and it is reporting these measurements back to the network, and in this case back to the MTSO. So the MTSO will take these measurements and now say that, okay, this user has now moved to a point where the signal from this base station is much larger than the signal from this base station, so let's do a handover procedure in which case the user is now allocated a traffic channel from this base station, and the traffic channel that was allocated from the previous base station is toned down. So this has to be done in a manner that the user does not feel the change in the traffic channel. So continuously, when you're communicating and you're moving, without interrupting the call, the handover procedure will shift you from one base station to another base station. And that is referred to as handover. And you will notice that if you're talking on the phone as you're traveling on the train out of the city, you see that the base station that you are communicating is constantly changing. Okay, now there is something called the MTSO also has to do with other situations where maybe a call is blocked, call is dropped, and so forth. Okay, now we've already done a little bit of traffic engineering because we saw this. Most networks, there are two types of networks. There are networks that are referred to as blocking networks, and there are networks that are referred to as non-blocking networks. A non-block, if all of the users in a network can be provided a traffic channel, that is referred to as a non-blocking network. But a non-blocking network is a theoretical network. It is impossible to achieve a non-blocking network in most cases because usually it's very expensive to achieve a non-blocking network. So most networks are blocking networks because the number of subscribers who are active at any one time usually is much larger than the number of channels. So you have to, this is where the concept of blocking probability comes. We saw in the previous example, there's a concept of blocking probability, which means what is the probability that a call during busy hour, what is the probability that a call will be blocked? And the Erlang's formula that we saw earlier in the table is based on this formula, which you might have seen in one of your earlier subjects in telecommunications, that the Erlang came up with this formula which gives you an expression between the probability of blocking, the traffic A in Erlang's, and N being the number of channels that are available, or number of servers, or number of channels that is available. Now, this is the actual mathematical formula, but most of the time, this formula is tabulated, and the table that you saw earlier, that I gave you on the back of that sheet, gives the number of servers or number of channels on the vertically, and the blocking probability horizontally. And if you know the blocking probability and the number of servers, you can work out the number of Erlangs that can be carried by the network. You can also, if you know the Erlangs And the blocking probability, you can also work out the number of servers or number of channels that you need to carry that. So usually, if I have a question for you in the exam, by the way, can you bring that Erlang table that I gave you today? Can you bring that to the exam, because that will help. You can use that same table in the exam. Okay, the other thing that we talked about, is spectral efficiency. Spectral efficiency is a measure of how efficiently you're using the spectrum, and it's usually measured in Erlangs per kilometer squared per hertz or per megahertz. Some people express it in megahertz, Erlangs per kilometer squared per megahertz. Some people measure it in hertz, but it's the same thing. It's an indication of how efficiently. So basically what you want to do is, as within how efficiently are you able to carry traffic with a limited frequency spectrum. Okay, and the last thing that I briefly want to tell you is that cellular systems have gone from first generation to second generation to 2.5 generation, 3G, and now 4G networks are coming up. There's been a lot of technology that has changed over a period of time. The first generation, the first mobile telecommunication systems that came out were predominantly analog cellular systems. They used FDMA-based system. Examples were AMS and the Nordic mobile telephone system in Europe. The second generation systems were examples being GSM. They were digital. Okay, so there was a big change from analog to digital, and as a result of moving to digital, we could incorporate a lot of security technologies like encryption and so forth, and also the quality improved. These second generation systems were primarily TDMA and CDMA based systems. They were primarily, both first generation and second generations were circuit switch technologies. And then came the 2.5 generation technologies like GPRS were 2.5 because they were considered halfway between 2G and 3G. And here packet switching was added to 2G networks. And you have a whole lecture on GPRS. As I said, after your midterm exam, the next lecture after that is GSM, where you'll go into more details about 2G. And the lecture after that is on GPRS, where you'll have more details about GPRS. And the last thing is the 3G technology. Okay, I'm gonna stop here for today. There are some more information given in your slides.